The second law of thermodynamics states that the entropy of an isolated system never decreases, because isolated systems always evolve toward thermodynamic equilibrium, a state with maximum entropy. The second law is an empirically validated postulate of thermodynamics. In classical thermodynamics, the second law is a basic postulate defining the concept of thermodynamic entropy, applicable to any system involving measurable heat transfer. In statistical thermodynamics, the second law is a consequence of unitarity in quantum mechanics. In statistical mechanics, information entropy is defined from information theory, known as the Shannon entropy. In the language of statistical mechanics, entropy is a measure of the number of alternative microscopic configurations corresponding to a single macroscopic state. The second law refers to increases in entropy that can be analyzed into two varieties, due to dissipation of energy and due to dispersion of matter. One may consider a compound thermodynamic system that initially has interior walls that restrict transfers within it. The second law refers to events over time after a thermodynamic operation on the system, that allows internal heat transfers, removes or weakens the constraints imposed by its interior walls, and isolates it from the surroundings. As for dissipation of energy, the temperature becomes spatially homogeneous, regardless of the presence or absence of an externally imposed unchanging external force field. As for dispersion of matter, in the absence of an externally imposed force field, the chemical concentrations also become as spatially homogeneous as is allowed by the permeabilities of the interior walls. Such homogeneity is one of the characteristics of the state of internal thermodynamic equilibrium of a thermodynamic system. The second law may be expressed in many specific ways, but the first formulation is credited to the French scientist Sadi Carnot in 1824. Introduction. The first law of thermodynamics provides the basic definition of thermodynamic energy, also called internal energy, associated with all thermodynamic systems, but unknown in classical mechanics, and states the rule of conservation of energy in nature. The concept of energy in the first law does not, however, account for the observation that natural processes have a preferred direction of progress. The first law is symmetrical with respect to the initial and final states of an evolving system. But the second law asserts that a natural process runs only in one sense, and is not reversible. For example, heat always flows spontaneously from hotter to colder bodies, and never the reverse, unless external work is performed on the system. The key concept for the explanation of this phenomenon through the second law of thermodynamics is the definition of a new physical quantity, the entropy. For mathematical analysis of processes, entropy is introduced as follows. In a fictive reversible process, an infinitesimal increment in the entropy of a system results from an infinitesimal transfer of heat to a closed system divided by the common temperature of the system and the surroundings which supply the heat. The zeroth law of thermodynamics in its usual short statement allows recognition that two bodies in a relation of thermal equilibrium have the same temperature, especially that a test body has the same temperature as a reference thermometric body. For a body in thermal equilibrium with another, there are indefinitely many empirical temperature scales, in general respectively depending on the properties of a particular reference thermometric body. The second law allows a distinguished temperature scale, which defines an absolute, thermodynamic temperature, independent of the properties of any particular reference thermometric body. Various statements of the law, the second law of thermodynamics, may be expressed in many specific ways. The most prominent classical statements being the statement by Rudolf Clausius, the statement by Lord Kelvin, and the statement in axiomatic thermodynamics by Konstantin Karaulther copyright O'Dory. These statements cast the law in general physical terms, citing the impossibility of certain processes. The Clausius and the Kelvin statements have been shown to be equivalent. Carnot's principle. The historical origin of the second law of thermodynamics was in Carnot's principle. It refers to a cycle of a Carnot engine, fictively operated in the limiting mode of extreme slowness known as quasi-static, so that the heat and work transfers are between subsystems that are always in their own internal states of thermodynamic equilibrium. The Carnot engine is an idealized device of special interest to engineers who were concerned with the efficiency of heat engines. Carnot's principle was recognized by Carnot at a time when the caloric theory of heat was seriously considered, before the recognition of the first law of thermodynamics, and before the mathematical expression of the concept of entropy. Interpreted in the light of the first law, it is physically equivalent to the second law of thermodynamics, and remains valid today. It states, the efficiency of a quasi-static or reversible Carnot cycle depends only on the temperatures of the two heat reservoirs, and is the same, whatever the working substance. A Carnot engine operated in this way is the most efficient possible heat engine using those two temperatures. Clausius Statement. The German scientist Rudolf Clausius laid the foundation for the second law of thermodynamics in 1850 by examining the relation between heat transfer and work. His formulation of the second law, which was published in German in 1854, is known as the Clausius Statement. Heat can never pass from a colder to a warmer body without some other change, connected therewith, occurring at the same time. Heat cannot spontaneously flow from cold regions to hot regions without external work being performed on the system, which is evident from ordinary experience of refrigeration, for example. In a refrigerator, heat flows from cold to hot, but only when forced by an external agent, the refrigeration system. Kelvin Statement. Lord Kelvin expressed the second law as, it is impossible, by means of inanimate material agency, to derive mechanical effect from any portion of matter by cooling it below the temperature of the coldest of the surrounding objects. Equivalence of the Clausius and the Kelvin statements. Suppose there is an engine violating the Kelvin statement, that is, one that drains heat and converts it completely into work in a cyclic fashion without any other result. Now pair it with a reversed Carnot engine as shown by the graph. The net and sole effect of this newly created engine consisting of the two engines mentioned is transferring heat from the cooler reservoir to the hotter one, which violates the Clausius statement. Thus a violation of the Kelvin statement implies a violation of the Clausius statement, that is the Clausius statement implies the Kelvin statement. We can prove in a similar manner that the Kelvin statement implies the Clausius statement, and hence the two are equivalent. Planck's proposition. Planck offered the following proposition as derived directly from experience. This is sometimes regarded as his statement of the second law, but he regarded it as a starting point for the derivation of the second law. It is impossible to construct an engine which will work in a complete cycle, and produce no effect except the raising of a weight and cooling of a heat reservoir. Relation between Kelvin's statement and Planck's proposition. It is almost customary in textbooks to speak of the Kelvin-Planck statement of the law. For example, c. 1 text gives a statement that for all the world looks like Planck's proposition, but attributes it to Kelvin without mention of Planck. One monograph quotes Planck's proposition as the Kelvin-Planck formulation, the text naming Kelvin as its author, though it correctly cites Planck in its references. The reader may compare the two statements quoted just above here. Planck's statement. Planck stated the second law as follows. Every process occurring in nature proceeds in the sense in which the sum of the entropies of all bodies taking part in the process is increased. In the limit, that is for reversible processes, the sum of the entropies remains unchanged. Principle of Carnot copyright Odori. Konstantin Carnot copyright Odori formulated thermodynamics on a purely mathematical axiomatic foundation. His statement of the second law is known as the principle of Carnot copyright Odori, which may be formulated as follows. In every neighborhood of any state S of an adiabatically enclosed system there are states inaccessible from S. With this formulation he described the concept of adiabatic accessibility for the first time and provided the foundation for a new subfield of classical thermodynamics, often called geometrical thermodynamics. It follows from Carnot copyright Odori's principle that quantity of energy quasi-statically transferred as heat is a holonomic process function, in other words. Though it is almost customary in textbooks to say that Carnot copyright Odori's principle expresses the second law and to treat it as equivalent to the Clausius or to the Kelvin-Planck statements, such is not the case. To get all the content of the second law, Co-author copyright O'Dory's principle needs to be supplemented by Planck's principle, that isochoric work always increases the internal energy of a closed system that was initially in its own internal thermodynamic equilibrium. Planck's principle. In 1926 Max Planck wrote an important paper on the basics of thermodynamics. He indicated the principle. The internal energy of a closed system is increased by an adiabatic process, throughout the duration of which, the volume of the system remains constant. This formulation does not mention heat and does not mention temperature, nor even entropy, and does not necessarily implicitly rely on those concepts, but it implies the content of the second law. A closely related statement is that frictional pressure never does positive work. Using a now obsolete form of words, Planck himself wrote, "The production of heat by friction is irreversible." Not mentioning entropy, this principle of Planck is stated in physical terms. It is very closely related to the Kelvin statement given just above. Nevertheless, this principle of Planck is not actually Planck's preferred statement of the second law, which is quoted above, in a previous subsection of the present section of this present article, and relies on the concept of entropy. The link to Kelvin's statement is illustrated by an equivalent statement by Elchvidian and Nieuwenhuizen, which they attribute to Kelvin. No work can be extracted from a closed equilibrium system during a cyclic variation of a parameter by an external source. Statement for a system that is a known expression of its internal energy is a function of its extensive state variables. The second law has been shown to be equivalent to the internal energy U being a weakly convex function, when written as a function of extensive properties. Gravitational systems. In non-gravitational systems, objects always have positive heat capacity, meaning that the temperature rises with energy. Therefore, when energy flows from a high-temperature object to a low-temperature object, the source temperature is decreased while the sink temperature is increased. Hence temperature differences tend to diminish over time. However, this is not always the case for systems in which the gravitational force is important. The most striking examples are black holes, which according to theory have negative heat capacity. The larger the black hole, the more energy it contains, but the lower its temperature. Thus, the supermassive black hole in the center of the Milky Way is supposed to have a temperature of 10 or 14 kelvins, much lower than the cosmic microwave background temperature of 2.7 kelvins, but as it absorbs photons of the cosmic microwave background its mass is increasing so that its low temperature further decreases with time. For this reason, gravitational systems tend towards non-even distribution of mass and energy. The universe in large scale is importantly a gravitational system, and the second law may therefore not apply to it. Corollaries. Perpetual motion of the second kind. Before the establishment of the second law, many people who were interested in inventing a perpetual motion machine had tried to circumvent the restrictions of First Law of Thermodynamics by extracting the massive internal energy of the environment as the power of the machine. Such a machine is called a perpetual motion machine of the second kind. The second law declared the impossibility of such machines. Carnot Theorem. Carnot's theorem is a principle that limits the maximum efficiency for any possible engine. The efficiency solely depends on the temperature difference between the hot and cold thermal reservoirs. Carnot's theorem states, all irreversible heat engines between two heat reservoirs are less efficient than a Carnot engine operating between the same reservoirs. All reversible heat engines between two heat reservoirs are equally efficient with a Carnot engine operating between the same reservoirs. In his ideal model, the heat of caloric converted into work could be reinstated by reversing the motion of the cycle, a concept subsequently known as thermodynamic reversibility. Carnot however further postulated that some caloric is lost, not being converted to mechanical work. Hence no real heat engine could realize the Carnot cycle's reversibility and was condemned to be less efficient. Though formulated in terms of caloric, rather than entropy, this was an early insight into the second law. Clausius inequality. The Clausius theorem states that in a cyclic process, the equality holds in the reversible case and the opening angle bracket is in the irreversible case. The reversible case is used to introduce the state function entropy. This is because in cyclic processes the variation of a state function is zero from state functionality. Thermodynamic temperature. For an arbitrary heat engine, the efficiency is where A is the work done per cycle. Thus the efficiency depends only on QC/QH. Carnot's theorem states that all reversible engines operating between the same heat reservoirs are equally efficient. Thus, any reversible heat engine operating between temperatures T1 and T2 must have the same efficiency, that is to say, the efficiency is the function of temperatures only. In addition, a reversible heat engine operating between temperatures T1 and T3 must have the same efficiency as one consisting of two cycles, one between T1 and another temperature T2, and the second between T2 and T3. This can only be the case if. Now consider the case where is a fixed reference temperature, the temperature of the triple point of water. Then for any T2 and T3. Therefore if thermodynamic temperature is defined by, then the function f, viewed as a function of thermodynamic temperature, is simply, and the reference temperature T1 will have the value 273.16. Entropy. According to the Clausius equality, for a reversible process, that means the line integral is path independent. So we can define a state function S called entropy, which satisfies. With this we can only obtain the difference of entropy by integrating the above formula. To obtain the absolute value, we need the third law of thermodynamics, which states that S equals 0 at absolute zero for perfect crystals. For any irreversible process, since entropy is a state function, we can always connect the initial and terminal status with an imaginary reversible process and integrating on that path to calculate the difference in entropy. Now reverse the reversible process and combine it with the said irreversible process. Applying Clausius inequality on this loop. Thus, where the equality holds if the transformation is reversible. Notice that if the process is an adiabatic process, then, so. Energy, available useful work. An important and revealing idealized special case is to consider applying the second law to the scenario of an isolated system, made up of two parts, a subsystem of interest, and the subsystem's surroundings. These surroundings are imagined to be so large that they can be considered as an unlimited heat reservoir at temperature Tr and pressure Pr so that no matter how much heat is transferred to the subsystem, the temperature of the surroundings will remain Tr. And no matter how much the volume of the subsystem expands, the pressure of the surroundings will remain Pr. Whatever changes to ds and dsr occur in the entropies of the subsystem and the surroundings individually. According to the second law, the entropy stat of the isolated total system must not decrease. According to the first law of thermodynamics, the change due in the internal energy of the subsystem is the sum of the heat IQ added to the subsystem, less any work IW done by the subsystem, plus any net chemical energy entering the subsystem dAI 1/4 IRNI, so that where I 1/4 IR are the chemical potentials of chemical species in the external surroundings. Now the heat leaving the reservoir and entering the subsystem is where we have first used the definition of entropy in classical thermodynamics. And then the second law inequality from above. It therefore follows that any net work IW done by the subsystem must obey. It is useful to separate the work IW done by the subsystem into the useful work IW that can be done by the subsystem, over and beyond the work PRDV done merely by the subsystem expanding against the surrounding external pressure, giving the following relation for the useful work that can be done. It is convenient to define the right-hand side as the exact derivative of a thermodynamic potential, called the availability or exergy of the subsystem. The second law therefore implies that for any process which can be considered as divided simply into a subsystem, and an unlimited temperature and pressure reservoir with which it is in contact, that is the change in the subsystem's exergy plus the useful work done by the subsystem must be less than or equal to zero. In sum, if a proper infinite reservoir-like reference state is chosen as the system's surroundings in the real world, then the second law predicts a decrease in E for an irreversible process and no change for a reversible process. Is equivalent to This expression together with the associated reference state permits a design engineer working at the macroscopic scale to utilize the second law without directly measuring or considering entropy change in a total isolated system. Those changes have already been considered by the assumption that the system under consideration can reach equilibrium with the reference state without altering the reference state. An efficiency for a process or collection of processes that compares it to the reversible ideal may also be found. This approach to the second law is widely utilized in engineering practice, environmental accounting, systems ecology, and other disciplines. History. The first theory of the conversion of heat into mechanical work is due to Nicolas La copyright Anard Sadi Carnot in 1824. He was the first to realize correctly that the efficiency of this conversion depends on the difference of temperature between an engine and its environment. Recognizing the significance of James Prescott Joules's work on the conservation of energy, Rudolf Clausius was the first to formulate the second law during 1850. In this form, heat does not flow spontaneously from cold to hot bodies. While common knowledge now, this was contrary to the caloric theory of heat popular at the time, which considered heat as a fluid. From there he was able to infer the principle of Sadi Carnot and the definition of entropy. Established during the 19th century, the Kelvin-Planck statement of the second law says, "It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work." This was shown to be equivalent to the statement of Clausius. The ergodic hypothesis is also important for the Boltzmann approach. It says that, over long periods of time, the time spent in some region of the phase space of microstates with the same energy is proportional to the volume of this region, that is that all accessible microstates are equally probable over a long period of time. Equivalently, it says the time average and average over the statistical ensemble are the same. It has been shown that not only classical systems but also quantum mechanical ones tend to maximize their entropy over time. Thus the second law follows, given initial conditions with low entropy. More precisely, it has been shown that the local von Neumann entropy is at its maximum value with a very high probability. The result is valid for a large class of isolated quantum systems. While the full system is pure and therefore does not have any entropy, the entanglement between gas and container gives rise to an increase of the local entropy of the gas. This result is one of the most important achievements of quantum thermodynamics. Today, much effort in the field is attempting to understand why the initial conditions early in the universe were those of low entropy, as this is seen as the origin of the second law. In formal descriptions, the second law can be stated in various succinct ways, including, it is impossible to produce work in the surroundings using a cyclic process connected to a single heat reservoir. It is impossible to carry out a cyclic process using an engine connected to two heat reservoirs that will have as its only effect the transfer of a quantity of heat from the low-temperature reservoir to the high-temperature reservoir. If thermodynamic work is to be done at a finite rate, free energy must be expended. Mathematical descriptions. In 1856, the German physicist Rudolf Clausius stated what he called the second fundamental theorem in the mechanical theory of heat in the following form. Where Q is heat, T is temperature and N is the equivalence value of all uncompensated transformations involved in a cyclical process. Later, in 1865, Clausius would come to define equivalence value as entropy. On the heels of this definition, that same year, the most famous version of the second law was read in a presentation at the Philosophical Society of Zurich on April 24, in which, in the end of his presentation, Clausius concludes, "The entropy of the universe tends to a maximum." This statement is the best-known phrasing of the second law. Because of the looseness of its language, for example universe, as well as lack of specific conditions, for example open, closed, or isolated, many people take this simple statement to mean that the second law of thermodynamics applies virtually to every subject imaginable. This, of course, is not true. This statement is only a simplified version of a more extended and precise description. In terms of time variation, the mathematical statement of the second law for an isolated system undergoing an arbitrary transformation is where S is the entropy of the system and T is time. The equality sign holds in the case that only reversible processes take place inside the system. If irreversible processes take place, the sign holds. An alternative way of formulating of the second law for isolated systems is, with the sum of the rate of entropy production by all processes inside the system. The advantage of this formulation is that it shows the effect of the entropy production. The rate of entropy production is a very important concept since it determines the efficiency of thermal machines. Multiplied with ambient temperature, it gives the so-called dissipated energy. The expression of the second law for closed systems is, here, is the heat flow into the system, is the temperature at the point where the heat enters the system. If heat is supplied to the system at several places, we have to take the algebraic sum of the corresponding terms. For open systems, here is the flow of entropy into the system associated with the flow of matter entering the system. It should not be confused with the time derivative of the entropy. If matter is supplied at several places, we have to take the algebraic sum of these contributions. Statistical mechanics gives an explanation for the second law by postulating that a material is composed of atoms and molecules which are in constant motion. A particular set of positions and velocities for each particle in the system is called a microstate of the system, and because of the constant motion, the system is constantly changing its microstate. Statistical mechanics postulates that, in equilibrium, each microstate that the system might be in is equally likely to occur, and when this assumption is made, it leads directly to the conclusion that the second law must hold in a statistical sense. That is, the second law will hold on average, with a statistical variation on the order of 1 per n, where n is the number of particles in the system. For everyday situations, the probability that the second law will be violated is practically zero. However, for systems with a small number of particles, thermodynamic parameters, including the entropy, may show significant statistical deviations from that predicted by the second law. Classical thermodynamic theory does not deal with these statistical variations. Derivation from statistical mechanics. Due to Loschmidt's paradox, derivations of the second law have to make an assumption regarding the past, namely that the system is uncorrelated at some time in the past. This allows for simple probabilistic treatment. This assumption is usually thought as a boundary condition, and thus the second law is ultimately a consequence of the initial conditions somewhere in the past, probably at the beginning of the universe, though other scenarios have also been suggested. Given these assumptions, in statistical mechanics, the second law is not a postulate, rather it is a consequence of the fundamental postulate, also known as the equal prior probability postulate, so long as one is clear that simple probability arguments are applied only to the future, while for the past there are auxiliary sources of information which tell us that it was low entropy. The first part of the second law, which states that the entropy of a thermally isolated system can only increase as a trivial consequence of the equal prior probability postulate, if we restrict the notion of the entropy to systems in thermal equilibrium. The entropy of an isolated system in thermal equilibrium containing an amount of energy of is, where is the number of quantum states in a small interval between and. Here is a macroscopically small energy interval that is kept fixed. Strictly speaking, this means that the entropy depends on the choice of. However, in the thermodynamic limit, the specific entropy does not depend on. Suppose we have an isolated system whose macroscopic state is specified by a number of variables. These macroscopic variables can, for example, refer to the total volume, the positions of pistons in the system, etc. Then will depend on the values of these variables. If a variable is not fixed, then because all the accessible states are equally likely in equilibrium, the free variable in equilibrium will be such that is maximized as that is the most probable situation in equilibrium. If the variable was initially fixed to some value, then upon release and when the new equilibrium has been reached, the fact the variable will adjust itself so that is maximized, implies that the entropy will have increased or it will have stayed the same. Suppose we start from an equilibrium situation and we suddenly remove a constraint on a variable. Then right after we do this, there are a number of accessible microstates, but equilibrium has not yet been reached, so the actual probabilities of the system being in some accessible state are not yet equal to the prior probability of. We have already seen that in the final equilibrium state, the entropy will have increased or have stayed the same relative to the previous equilibrium state. Boltzmann's H theorem, however, proves that the quantity H increases monotonically as a function of time during the intermediate out of equilibrium state. Derivation of the entropy change for reversible processes. The second part of the second law states that the entropy change of a system undergoing a reversible process is given by, where the temperature is defined as. See here for the justification for this definition. Suppose that the system has some external parameter, x, that can be changed. In general, the energy eigenstates of the system will depend on x. According to the adiabatic theorem of quantum mechanics, in the limit of an infinitely slow change of the system's Hamiltonian, the system will stay in the same energy eigenstate and thus change its energy according to the change in energy of the energy eigenstate it is in. The generalized force, x, corresponding to the external variable x is defined such that is the work performed by the system if x is increased by an amount dx. For example, if x is the volume, then x is the pressure. The generalized force for a system known to be an energy eigenstate is given by. Since the system can be in any energy eigenstate within an interval of, we define the generalized force for the system as the expectation value of the above expression. To evaluate the average, we partition the energy eigenstates by counting how many of them have a value for within a range between and. Calling this number, we have. The average defining the generalized force can now be written. We can relate this to the derivative of the entropy W at E. X at constant energy E as follows. Suppose we change x to x plus dx. Then will change because the energy eigenstates depend on x, causing energy eigenstates to move into or out of the range between and. Let's focus again on the energy eigenstates for which lies within the range between and. Since these energy eigenstates increase in energy by y dx, all such energy eigenstates that are in the interval ranging from y dx to E move from below E to above E. There are such energy eigenstates. If all these energy eigenstates will move into the range between and contribute to an increase in the number of energy eigenstates that move from below to above is, of course, given by the difference. Is thus the net contribution to the increase in. Note that if y dx is larger, then there will be the energy eigenstates that move from below E to above. They are counted in both and, therefore the above expression is also valid in that case. Expressing the above expression as a derivative W at E. E in summing over y yields the expression. The logarithmic derivative of W at E. X is thus given by. The first term is intensive, that is, it does not scale with system size. In contrast, the last term scales as the inverse system size and will thus vanishes in the thermodynamic limit. We have thus found that combining this with gives derivation for systems described by the canonical ensemble. If a system is in thermal contact with a heat bath at some temperature T, then, in equilibrium, the probability distribution over the energy eigenvalues are given by the canonical ensemble. Here Z is a factor that normalizes the sum of all the probabilities to 1. This function is known as the partition function. We now consider an infinitesimal reversible change in the temperature and in the external parameters on which the energy levels depend. It follows from the general formula for the entropy that inserting the formula for the canonical ensemble and here gives general derivation from unitarity of quantum mechanics. The time development operator in quantum theory is unitary, because the Hamiltonian is Hermitian. Consequently, the transition probability matrix is doubly stochastic, which implies the second law of thermodynamics. This derivation is quite general, based on the Shannon entropy, and does not require any assumptions beyond unitarity, which is universally accepted. It is a consequence of the irreversibility or singular nature of the general transition matrix. Non-equilibrium states, it is only by convention, for the purposes of thermodynamic analysis, that any arbitrary occasion of spacetime is said to be in thermodynamic equilibrium. In general, An occasion of space-time found in nature is not in thermodynamic equilibrium, read in the most stringent terms. In looser terms, nothing in the entire universe is or has ever been truly in exact thermodynamic equilibrium. If it is assumed, for the purposes of physical analysis, that one is dealing with a system in thermodynamic equilibrium, then statistically it is possible for that system to achieve moments of non-equilibrium. In some statistically unlikely events, hot particles steal the energy of cold particles, enough that the cold side gets colder and the hot side gets hotter, for a very brief time. A physics involved in such events is beyond the scope of classical equilibrium thermodynamics, and is the topic of the Fluctuation Theorem. This was first proved by Botchov and Kossovlev, and later by Evans and Searles. It gives a numerical estimate of the probability that a system away from equilibrium will have a certain change in entropy over a certain amount of time. The theorem is proved with the exact time reversible dynamical equations of motion but assumes the axiom of causality, which is equivalent to assuming uncorrelated initial conditions. Such events have been observed at a small enough scale where the likelihood of such a thing happening is significant. Quantitative predictions of this theorem have been confirmed in laboratory experiments by use of optical tweezers apparatus. Arrow of time. The second law of thermodynamics is a physical law that is not symmetric to reversal of the time direction. The second law has been proposed to supply an explanation of the difference between moving forward and backwards in time, such as why the cause precedes the effect. Controversies. Maxwell's demon. James Clerk Maxwell imagined one container divided into two parts, A and B. Both parts are filled with the same gas at equal temperatures and placed next to each other. Observing the molecules on both sides, an imaginary demon guards a trapdoor between the two parts. When a faster-than-average molecule from A flies towards the trapdoor, the demon opens it, and the molecule will fly from A to B. The average speed of the molecules in B will have increased while in A they will have slowed down on average. Since average molecular speed corresponds to temperature, the temperature decreases in A and increases in B, contrary to the second law of thermodynamics. One of the most famous responses to this question was suggested in 1929 by Lee Kubert-Zeiler R.D. and later by La copyright on Brillouin. Zeiler D. pointed out that a real-life Maxwell's demon would need to have some means of measuring molecular speed, and that the act of acquiring information would require an expenditure of energy. Maxwell's demon repeatedly alters the permeability of the wall between A and B. It is therefore performing thermodynamic operations, not just presiding over natural processes. Loschmidt's paradox. Loschmidt's paradox, also known as the reversibility paradox, is the objection that it should not be possible to deduce an irreversible process from time-symmetric dynamics. This puts the time reversal symmetry of nearly all known low-level fundamental physical processes at odds with any attempt to infer from them the second law of thermodynamics, which describes the behavior of macroscopic systems. Both of these are well-accepted principles in physics, with sound observational and theoretical support, yet they seem to be in conflict. Hence the paradox. One proposed resolution of this paradox is as follows. The Loschmidt scenario refers to a strictly isolated system or to a strictly adiabatically isolated system. Heat and matter transfers are not allowed. The Loschmidt reversal times are fantastically long, far longer than any laboratory isolation of the required degree of perfection could be maintained in practice. In this sense, the Loschmidt scenario will never be subjected to empirical testing. Also in this sense, the second law, stated for an isolated system, will never be subjected to empirical testing. A system, supposedly perfectly isolated, in strictly perfect thermodynamic equilibrium, can be observed only once in its entire life, because the observation must break the isolation. Two observations would be needed to check empirically for a change of state, one initial and one final. When transfer of heat or matter are permitted, the requirements of perfection are not so tight. In practical laboratory reality, therefore, the second law can be tested only for systems with transfer of heat or matter, and not for isolated systems. Due to this paradox, derivations of the second law have to make an assumption regarding the past, namely that the system is uncorrelated at some time in the past or, equivalently, that the entropy in the past was lower than in the future. This assumption is usually thought as a boundary condition, and thus the second law is ultimately derived from the initial conditions of the Big Bang. Poincaré copyright recurrence theorem. The Poincaré copyright recurrence theorem states that certain systems will, after a sufficiently long time, return to a state very close to the initial state. The Poincaré copyright recurrence time is the length of time elapsed until the recurrence, which is of the order of. The result applies to physical systems in which energy is conserved. The recurrence theorem apparently contradicts the second law of thermodynamics, which says that large dynamical systems evolve irreversibly towards the state with higher entropy, so that if one starts with a low entropy state, the system will never return to it. There are many possible ways to resolve this paradox, but none of them is universally accepted. The most reasonable argument is that for typical thermodynamical systems the recurrence time is so large that, for all practical purposes, one cannot observe the recurrence. Quotations. The law that entropy always increases holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations then so much the worse for Maxwell's equations. If it is found to be contradicted by observation well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics I can give you no hope. There is nothing for it but to collapse in deepest humiliation. There have been nearly as many formulations of the second law as there have been discussions of it. Clausius is the author of the Sibyllic utterance, "The energy of the universe is constant. The entropy of the universe tends to a maximum." The objectives of continuum thermodynamics stop far short of explaining the universe, but within that theory we may easily derive an explicit statement in some ways reminiscent of Clausius, but referring only to a modest object, an isolated body of finite size. See also. References. Bibliography of citations. Further reading, Goldstein, Martin, and Injeff, 1993. The Refrigerator and the Universe. Harvard University Press. CHPTS. 4 €9 contain an introduction to the second law, one a bit less technical than this entry. ISBN 978-0-674-75324-2, Leff, Harvey S., and Rex, Andrew F. 2003. Maxwell's Demon Tool Entropy, Classical and Quantum Information, Computing. Bristol, UK. Philadelphia, PA, Institute of Physics. ISBN 978-0-585-49237-7, Halliwell, J.J. Physical Origins of Time Asymmetry. Cambridge. ISBN A0-521-56837-4, Technical. Carnot, Sadi. Thurston, Robert Henry. Reflections on the motive power of heat and on machines fitted to develop that power. New York, J. Wiley & Sons, Stephen J. Klein. The Lowdown on Entropy and Interpretive Thermodynamics, LaCour +/- CA, DCW Industries. ISBN 1928729010. Kostick, M., Revisiting the Second Law of Energy Degradation and Entropy Generation, From Sadi Carnot's Ingenious Reasoning to Holistic Generalization AIP Conf. Proc 1411, ppA 327 €350. doi, http://dx.org 1.3665247. American Institute of Physics, 2011. ISBN 978-0-7354-0985-9. Abstract at, 2. Full article, also at, 4. External links, Stanford Encyclopedia of Philosophy, Philosophy of Statistical Mechanics by Lawrence Sklar. Second Law of Thermodynamics in the MIT course Unified Thermodynamics and Propulsion from Professor Z. S. Spakovsky, E. T. Janes, 1988, The Evolution of Carnot's Principle, in G. J. Erickson and C. R. Smith Maximum Entropy and Bayesian Methods in Science and Engineering, Vol. 1, PA 267. Carathéodory, C. Examination of the Foundations of Thermodynamics, Trans. By D. H. Delfinish.